Okay, so welcome to the RISC-V workshop hosted by IEEE. So, um, RISC-V is a assembly level language, so to understand what assembly is, it's what the compiler gets after it compiles the C program, C++ program, or some other compile language. It takes the C program and compiles into something much simpler that the computer can much more easily understand. Um, hope all the values that are in a RISC-V program are stored in registers. Some of them we can access, like X5 through X7, X28 through X31. Those are temporary registers where a lot of our variables will be stored. X0 is the constant 0. The other registers are not too important. We're not going to be using them too much today, so I'm not going to spend too much time on them. So, um, the first really basic instructions are add and subtract. So taking the C code where f equals g plus h minus I plus j, so we can just simply add g and h into the temporary register T0 right now. We can then add I and j into T1, and then we can subtract T1 from T0 and put that into f. We can also access memory operands, which are used in arrays where the values are stored in memory instead of a register. So when we have to access something that's stored in a register, we have to multiply the offset by 4. So in this case, we have a index 8, so we'd make do multiply it by 32. So we have to load it from memory, which we use the load word command. So we're loading the 8th index of a into temporary register x8. We're then going to then add x8 and x2, where x2 is just h into x8, and then because we're storing that back into A12, we have to store that into the 12th index, which gives us multiply x3 by 48. So um, we can also deal with immediate operands, which are just constant values like 4, 8, any number. So we just use the add immediate command to add them. So if we wanted to increment x22 by 4, we would just add x22 and 4 back into x22. There is no subtract immediate command, so if we wanted to subtract a value as a constant, we would just use a negative value instead of using a sub I command, which doesn't exist in RISC-V. So another simple example here would just be f equals g plus h minus 5. Where h is stored in x1, g is stored in x2, and f is stored in x3. So, would anybody like to try and take a stab at this and tell me what the assembly code will be for this?
홍수진 다시 봐. 자기가 또 바꿔라. 또. नहीं झगड़ा करो 뭐 쉽게 쉽게. 컴퓨터 치는
Anybody like to try and take a look at this and see if they can figure out what the assembly instructions will be? Any volunteers? Anyone? Okay. So it's just add immediate h into minus 5 into x22, and then just add x3, or to add x2 and x22 into x3, which is f. There's also branch instructions, which we use for if statements, else, and different types of loops like while, for, do while. So we have our branch equal, which tests if two registers are equal to each other. Our branch not equal, which tests if two registers are not equal to each other. Our branch greater than, which just tests if two registers are greater than or equal to each other. And our less than, which just tests if a register is less than some other register. So right here, we're going to test if register 19 and 10 are equal to each other. If they are, then we're going to go to end all the way down at the bottom. If they're not, we just continue the cycle. So then we're going to add x10 and x18 back into x18, and then we're going to decrement x19 by 1. And then after we do that, we go to this J loop. So that loop just means go to that loop, and the J just means there's no condition. It will always do it. So whenever we hit that loop, it will always do it. However, if x19 and x10 are equal, then it skips those 3 lines and goes directly down to end. Now, here is a C instruction sample. While g is equal to f, h equals h plus f, and g equals g minus 1, which is the same as this other example here. And then our last instruction is our load immediate. We usually use this for initializing values. Most registers will be initialized to 0 if they're not being used. So if we want to load up a value at the beginning of the program, just say int x equals 5. We'll do load immediate register and then 5. So any questions before we move on? No? Okay. So I'm now going to go over this basic assembly program. So I'm going to be loading up, I'm going to be finding the sum of prime numbers between 0 and some number n. For this case, I'm just going to do it as 99. So I'm going to do load immediate x6 99. This is just going to initialize x6 as our limit. So when we hit 99, we're just going to stop doing it. I'm also going to initialize 2 other registers as 1. This will be for the beginning of our loop and to find the sum because 1 does not work with the prime number algorithm. We just have to assume that it is included. So I'm just going to make x28 our sum and then x29 the starting point of our loop. So again, I'm just going to do loop. So then I'm also going to load 2 into x5 that will set our initial value for the inner loop, which I'll just call loop 1. So what we're going to do is we're going to test if they're equal here. So if x5 and x6 are equal, then it is a prime number. Then I need to also find the remainder if I do division, because if a number can be divided equally by any number except 1 in itself, then it is not a prime number. So I'm also going to test if x7 here, which shows the result or a remainder, if it's equal to 0, then it is not a prime number. And then I'm also going to increment x5 by 1 just to go through the loop. If it is a prime number, what we're going to do is we're going to add x6 into x28. So x6 is just the actual prime number. Since we're finding the sum, we want to add that back in to our sum value here. And then we're also going to decrement x6 by 1. And then after that, we'll go back up to our original loop all the way at the top and start the iteration again until we hit our final number. And then if it is not a prime number, we're just going to decrement x6 by 1. We're not going to do anything involving adding it into the sum. And at the end of all that, if we get through and everything is done, then we're just going to have an exit command there. So if we run this, the total sum, middle of instruction. Oh. Oh, should be. Hold on. Ooh. Okay, that should not have happened. 1 second. 28. So now if I go to run it, it should be 1061 in x28. Wait, no, what's wrong there? just ran this earlier. Okay. So, Nick, do you want to start streaming and start taking over the other half of the workshop?
Yeah. So next up, we have an application for the general purpose input and output. So the pins that would be on a, we're going to use a high five board. So this comes from the class EC 395, the microprocessors lab. So the problem presented in the lab is that a maple syrup factory has a holding tank that tends to overflow, and they want to make an annunciator system. Annunciator is a device that provides information on the state of something. So what they want from the system is they want two indicators inside the tank. They want a full level alarm, which we'll call FLA, and an overflow level alarm, or OLA. Then for ease of interpretation for the person actually like sitting at the control panel, they want a green, a yellow, and a red LED to represent normal conditions, FLA, and OLA respectively. They also want a way of acknowledging, which we'll call ACK, when the system receives a signal. So well, from FLA or OLA, and a way of testing the system just to make sure they don't miss anything. And this test, the conditions they set is they want the green LED to stay solid and have the yellow and red LEDs flash. So before we even go into any coding, we need to understand like what we need to do first. So how many inputs does the system have? Because we need to know what pins need to be inputs and what pins need to be outputs. So based on this information, we need to receive information from FLA, we need to receive information from OLA, we need to receive information from the acknowledge, and we need to receive information from the test. So these are our 4 inputs for our code. And then what outputs do we need? Where does the system need to send a signal? We need to send the signal to the green LED, the yellow LED, and the red LED. And then we can make this much simpler for ourselves by setting up a state diagram. So our normal state we'll just call state B, which is everything's normal, it's not overflowing, it's not full, we're not pressing the test button, and it's just sitting at a green light. Now, we have different states. If we were to press the test button and it's not full, we would go to state A, which is green, flashing yellow, flashing red. And then once you release the test button, so not test, it'll go back to green. But now if we're here and we receive from the tank a full level alarm for FLA, then we would have it would start flashing yellow. Now, while it's flashing yellow, again, we want a way to acknowledge, like we want someone at the control panel to be able to acknowledge that it is becoming full. So while it's still FLA, and if we press the acknowledge button, we want it to be solid yellow. So it goes from flashing yellow to solid yellow. Then from here, we have a couple different options. If the level in the tank drops back down below FLA, it'll drop back to here and back to state C and then back to state B, and it'll be fine. It'll be sitting at green again. An alternative route from here is that, well, if it doesn't drop below FLA, but it keeps filling up, well, then it's going to start hitting the overflow. So then from state D, we would go down to state E, which is flashing red. And then from here, we would need to acknowledge it again. The person at the control panel would need to acknowledge the overflow, and we would go to solid red. And it would stay solid red until it drops back down below the overflow mark to state D. And then it would stay at state D until it drops back down below FLA and will go all the way back to state B. And backtracking, if we are at state C and it's flashing yellow and nobody acknowledges it, but it still goes above OLA, it will then go straight to flashing red. So this is going to be our actual process of our C code that I'll show now. So taking this information, we'll go into the code. So we need to set up a couple of things. We have a header file with all of our pin offsets, and all of these values come with, it's in the manual for your actual board. So based on the board I have, these are the offset pin values. And then from here, so we have a header file for the C file. Then we have include files that we would use for the .s files. And the .s files is where we would actually use the assembly language that Nick was showing us. So what we do here, real quick, I just want to point this out. Here, we set up an array of all of our input pins. We want to use pin 2, 4, 7, and 9 as our input pins. And then we want to use pins 17, 18, 19 as our output pins. And these are setting up the arrays. And then from there, just real quick, our setup GPIO, this is just actually setting the inputs as inputs and setting the outputs as outputs. And then this is just to make sure that the output starts at 0 so we don't have any conflicting data. The checkbot file, what this does is it checks our inputs. It checks if someone is pressing a test button, or if it checks if someone is, or if the tank filled to a FLA. This is what this does, it checks. The set LED is then the function that sets the LED on or off based on the inputs that were checked in checkbot. And then delay is just our delay when the lights are flashing. It's just something that happens within the code by itself. So now for the actual main code. So we just want this to repeat all the time. That's why we have the while loop. But then before we even go into the switch, what the switch is the most important part. First, we need to check if anything's being acknowledged. We need to check if if the test button's being pressed. We need to check FLA and OLA. Then based on these values, we then go into the switches. So we want to start at case B because from here, again, we want to start in the normal state. So we're going to start in case B. So we want pin 17, which we assigned to green, we want that on, and we want yellow and red off. And then if it becomes full, it's not acknowledged, and it's not overflowing, we go to case 3, or which is case C, which again would be flashing yellow. I'm not going to go through all of this because that would be very redundant, but that is what the switch does. The switch is a very easy way of going state by state from your state diagram. So that's why I said earlier, state diagram is very important because it makes the actual code much easier on you. So real quick, I'm going to turn on my webcam, stop sharing my screen. And I'll actually show the circuit I have in front of me. So I apologize for the angle, but so right now, nothing is happening, and you can see that the green LED is on, nothing's happening. This button is our acknowledge button. I guess that would be the leftmost. I don't know how the webcam picks that up. For me, it's my left. The one closest to LEDs is acknowledge. This button is our test, which I'll actually just show you right now. When I press and hold test, the green LED stays on. We have yellow and red flashing. And then we have a switch here. It has 2 switches on it. Switch 1, just for this simplicity of it, switch 1 was FLA. So while nothing's happening, if FLA occurs, our green light turned off and the yellow light starts flashing. Now, if I'm at the control panel and I see this yellow light flashing, well, I'm going to acknowledge that. So I'm going to press the acknowledge button, and it's going to become a solid yellow light. And then let's do the case, okay, it went to FLA and then it drops back down below. If it's no longer FLA, it drops back down to green, and everything's okay. Now in the event it's yellow, no one acknowledges anything, and then it goes to OLA. Now our red light's flashing, and I can acknowledge that as well, becomes solid red, and then if it drops back down to FLA only, and then back down to green. So that's how you would use RISC-V with a high 5 board in a somewhat real world application. I guess I'll hand it back to you, Nick.
Does anybody have any questions about either of the projects I just went over? Okay, then I guess that concludes our RISC-V workshop. Thank you for coming, everyone.